Welcome to Sober Math. In a previous video I showed you the envelope curve for string art, and there is a related curve for this falling ladder. Those videos are linked below, but the story didn't end there. Imagine an in-between possibility. So I bet you're awake now. And this is it, a loop of string in the shape of a right triangle. The string doesn't really stretch, but it helped to draw out this middle curve here. And does that curve look at all familiar? Looks like a quarter circle, doesn't it? But if that's the case, what's up with this scary formula? But notice that our blue ladder curve and our red string curve seem to surround that quarter circle. But then m equals 2/3 for the ladder curve and 1/2 for the string curve. And so we might expect that maybe there's some in-between number that might exactly capture this quarter circle. In blue, I've picked the ladder-like curve, and changing that value of m, we see it crosses that quarter circle, here in red. But for this m value, they look the same. So is that a quarter circle? If we zoom in, we can see that there is some difference. We could also narrow the x-range and see that the curves are different. Otherwise, we can subtract the two functions and plot the difference function. So to the naked eye, the ladder-like curve was a quarter circle, but they aren't exactly identical. But the value of m equals 0.562 gets us very close. So the string loop curve is not a ladder-like curve. But oddly enough, our formula for a circle works with m equals 2. So what's the discrepancy? Well, for this to be the case, that circle has to be centered at the origin, this point right here. But then for our string loop curve, the center is at r, r. To begin, take our string as a blue right triangle with sides a, b, and hypotenuse the square root of a squared plus b squared. Then our string length is the perimeter, a plus b plus the square root of a squared plus b squared. We solve for b, why not, and get the square root alone. Then square both sides. Then distribute that square and the b squareds cancel. Swap these terms, and now FOIL this square, and the a squareds cancel, and then isolate b and put it aside. Now we construct our circle diagram, and I'll argue that we get a consistent result. So if s is the length of the string, and we fold it in half, then s by 2 becomes the radius of the circle. We impose xy coordinates, and draw on our quarter circle, which has a radius r, and that green dot as the center. That green circle path is tangent to the string. So I draw this line segment passing through the tangent point from the green dot with length r to the tangent point. And these are perpendicular. Notice these orange angles are congruent. The radius at the top is r, and so this length is r minus a. This length is r minus a also. And I'll call this little distance d. The hope is to write all the quantities in terms of the constant s and a, and then cancel that a out somehow, and then get back the string perimeter equation. So duplicate the little triangle and flip it over, and then duplicate that large triangle and rotate 90 degrees, and then we clean up the diagram. These three right triangles are similar, and I label this opposite side, and its value is given by the Pythagorean theorem. We simplify under the radical. Remember that r is really s by 2. So plug this in and cancel the 2's and factor. We can write down this proportionality from the second and third triangles. And let's solve it for d. Again, r is s by 2, and plugging this in we get this. Now simplify that compound fraction. We cross multiply, and then square, and cancel this d. We cross multiply again, and distribute that s plus d, and move the d terms together to combine them. Factor the d, distribute the second term, the s squareds cancel, and isolate the d. Don't these appear similar? So why not write d in terms of b? And so we get this. And it turns out to be a shortcut. So put it aside, and from the first and third triangles, we write down this proportionality. And then write in terms of S, and then solve for D. What's next? Right, we get rid of D by combining, and we make a like denominator in that left term, and then combine steps and then cross out these denominators where A is non-zero. And we want to write this to look like the string perimeter equation. Distribute the B while moving BS over. Factor out the S, and that expression in parentheses looks close except for the minus signs. But we're not done. We get S by itself, and we have a square root in the denominator. So what now? This denominator is begging to be rationalized by this factor. And gradually stuff cancels. And then we get back that string perimeter equation. One thing might be bugging you. I started with the perimeter equation to solve for B, remember? So this is a demonstration but not a proof. And see the description below for a calculus-based method. So another quick demonstration. To begin, note that the center of our circle is at point H, K, which is located at R, R, where R is the radius of the circle. This is the form of the circle. And so we plug in and FOIL that square, cancel the R squareds. When we take the square root of both sides, we get a plus and a minus solution. By the diagram, y is less than r for our quarter circle, and y minus r is negative. And so we take the negative solution. Move that r over, and r equals s by 2. We plug in, and the 2's cancel, and we are seeing the square rooty expression in x. We swap these two, and get the square root of x times s minus x is s over 2 minus y. So the square root is written as a difference, and this will come in handy. By symmetry, we get the y counterpart. So here's that big rooty equation, which I claim is a quarter circle, and here's a more user-friendly form. And now all the rooty stuff is in orange and blue as P and Q respectively. Just look at all that pretty symmetry. But the rooty stuff can be written as those differences. So plugging those in, there. So the square roots are all gone. We FOIL out that second term and simplify the third and distribute that fourth. And check it out. Ready? XY's cancel. The x by 2's times x's cancel, as do the y counterparts. Almost there. So the double negatives are positive. Distribute and move terms around with all the s-only terms on the right-hand side. And what needs to be done here? Yes, we complete the square twice, once for x and a second time for the y. This leaves us with two subtracted squares, the price of completing a square, which we move and combine to the right-hand side. And there it is. We got back the circle equation with center at s by 2, s by 2. So the thing is, I could swear that I ruled out this possibility a long time ago. I found this very strange formula after several attempts, but I could swear that I had ruled out the possibility that, I mean, it's the first thing you'd want to try, right? To see if it's a circle. I thought I ruled it out a long time ago, and then I remembered falsely. So in the process of editing this video, I sort of rediscovered that this actually matches a perfect quarter circle to double precision. And so in mathematics, that's what we often find, is that there's some property or shortcut that becomes obvious in hindsight. And the derivation of this equation is definitely not obvious, but if you'd like to see it in a future video, please let me know in the comments. So in this video, we took the sum of the legs and the hypotenuse. In a future video, we take the difference in our taxicab curve. So please like and subscribe, and stay tuned for the final installment.